Yeah, so indeed, 5G and race cars. But we're in Italy, right? And some stereotypes, and this is from an Englishman who demanded tea yesterday. So like, it's there's a feeling that like maybe you're interested in fast cars and fast talking, and maybe a little willingness to bend the rules here in Italy. And that's kind of basically our agenda. That's what we're going to talk about. So start with the fast cars, which you've already heard, but like you can watch. Give you a full. So this is a recording, obviously, but it was live video from the pit of a car, I think going around Monza, quite fast on a practice day. And yeah, this is the purpose of this is it sits over the driver's shoulder, and the idea is to give audio and video feed at low latency and high quality back to the pit crew so that they can see, and particularly in case of driver training or where they're trying to adjust some aspect of the car remotely, they want to be able to see what's happening on the track at low latency. And like, obviously they're doing quite high speeds. And the range of this is such that like typically the car is a couple of kilometers away from the pit, which is just too far for doing Wi-Fi. And anyway, the thing is moving. So like aiming a directed Wi-Fi at it is a difficult game. So we're ending up using public networks, which is obviously 5G. But latency is critical. I mean, the instructor needs to be able to communicate with the driver about something that's like currently happening and not something that happened 6 seconds ago. And so and they're very sensitive to this. It's kind of interesting. I watched this. They know the latency because they can hear the car changing gear a couple of 100 meters away. And if you're out of sync with that, they will know. And not only that, but they're really aware of the engine pitch, right? So the thing that Chrome does, which is if it thinks it's lost a frame or two, it like fills in and goes a bit faster. That really upsets them. Like it's wrong. Okay, so you have to be quite cautious about like trying to make sure it's as real as possible. And we're aiming for 200 to 300 milliseconds. And you wonder why? Well, 200 milliseconds turns out to be the amount of cognitive impairment that the Americans allow the blood alcohol limit for drivers. And so that's a kind of bottom end. And then the top end is a set how long it takes the speed of sound for sound to get, say, 100 meters from the car to you. So that gives you a kind of a measure for it. But you might be wondering like how I got into this and who the hell I am actually. So I'm Tim Panton, I'm the CTO at Pipe GmbH, and Pipe licenses a WebRTC stack originally for baby monitors, security cameras, things like that. And we use a kind of patented authentication method which doesn't trust the center. There's no centralized database of people who can use it and stuff like that. It's done at the edges and verified at the edges. And we got asked like whether we could run this architecture in a race car, take it away from a baby monitor and put it in a race car. And in a moment of foolishness, I said yes. And that's been about the last year or year and a bit's worth of adventure. So what's different? Why isn't this just like a baby monitor? Why can't I just like take exactly what we're using in the 40,000 baby monitors that are out there and you know, just use it? And the answer is that 5G really isn't the same as Wi-Fi. And the source is moving. We kind of knew that. It's quite fast. And the consequence of that is the video is changing a lot faster than babies move. And so like the bit rate you need is quite high. And the other thing that we found is that the hardware is different. You kind of need to put a modem in there. You need to put a 5G modem in there. And that means you probably need an M2 slot. And so like that brings you to a different set of hardware configuration. So this is one of them. My engineer will be furious that you've seen the plastic one and that you haven't seen the beautiful aluminium one. But this is what I had in my bag when I came here, so that's what you get to see. It's a prototype. He has a much more beautiful thing that looks much more like at home in a race car than that does. But important things about it, though, is that it's an 8-core, 2 gigahertz ARM, which turns out to be vastly over what we really need. But like, it's what we've been offered is 32 gig of disk, 16 gig of RAM. I mean, I have servers that are smaller than this, but 30 frames a second camera in there, and at 1080p, and H.264 hardware encoder, and the whole thing draws around 7 watts, which actually for a thing that small means that you do need to think about that actually. And there's a you can probably just about see in that diagram that there's an M2 little modem with a heatsink on it sitting there. The big learning from this whole exercise is that there is actually no such thing as 5G. Like, there's a label, but it covers an absolute ton of different actual products. Like what you get when 5G lights up on your phone is a huge variety of stuff, not least because it's this wacky range of frequencies from about 600 megahertz to 23 gigahertz, right? And those are all 5G frequencies. And they have wildly different properties. I mean, a lot of them don't even go through toughened glass, let alone a steel roof or something like that. And then as a result of that, you get a wild variety of bit rates from it. And the pricing is just like surreal. So what I should have done when I came here, but I actually forgot to do it, is to buy a local SIM when you get here, and then buy an all-you-can-eat plan for a day, which typically costs about 8 or 10 euros. And then I can get through as many gigabytes as I like in a day, and actually it works really well. And then there's this whole business with SA and NSA, which I kind of almost don't want to talk about, but like catch me over tea in a bit or something. And there's a ton of different network topologies that you might end up with. So like, I have a wish list on the left of the things I really want. And the key one is I'd like IPv6, please, and I'd like it routable. And it would be really nice if I got that IPv6 address in the same country as the racetrack. And what I normally get is an IPv4 that's in some other country. And so I end up with another few hundred milliseconds of latency, or tens of milliseconds of latency. It depends on which SIM you buy and who it's from, and like random stuff. And I'd love gigabits really, but actually realistically, I'm going to get megabits. So hard numbers performance thing. Like the bottom line is it's better than 4G. Like it is noticeably better than 4G. We get about 20 milliseconds less latency on a 5G connection than a 4G connection, typically. It's quite variable, that. But we'd sort of get, it looks like around 80 milliseconds latency. And we end up with a glass-to-glass latency of about 320 milliseconds. And there's a separate project I did, which open source project called glass-to-glass, which is open source hardware and open source software for measuring glass-to-glass latency in video cameras. So, I mean, and it will work. I've actually done a little bit of testing on SFUs as well, which is interesting. And amusingly, out of that, I discovered that Safari is, or maybe was, because I mentioned it to a Chrome engineer, Safari is 30 milliseconds faster than Chrome at rendering at H.264. So that may actually, in some future update, that may get fixed because I mentioned it. But it's kind of weird, unexpected. So you do need to measure stuff to find these things out. The bandwidth I get out of 5G typically is around 4 times what I get out of LTE. So typically 200 down, 40 up. And given that I only need 2.5 to 5, something like that, megabits a second to get decent video, that's actually fine. Now, decent video is predicated on me being clever about how we do things like keyframe intervals and how we do NAT PLI. And we'll talk a little bit more about that in a moment. But the big summary is that it's comparable to what I was getting in fiber to the cabinet. only it works at 200 kph, which is like actually pretty cool, realistically. I mean, the radio from 5G is amazing. Like the rest of it is a bit flaky, but like the radio is really cool. And the downside to all this is because the thing is moving, we get wildly big swings in the available video bandwidth. This particular graph is from a car going around a track somewhere. I don't actually remember where now. Over a space of about an hour, and in that time, it cell hopped, I think 70 times, and half the time it was on 4G and half the time it was on 5G. So like we get these wild variations, not only as part of the cell hopping, but also because we're on switching from 4 to 5G. So we have to be quite clever about how we're handling it. And the standard kind of WebRTC tricks mostly work. We just have to be a bit more aggressive about them. I mean, the obvious thing that WebRTC does is that it infers network queuing by looking at the real time, the round trip time, and deduces that there is a queue building up because the round trip time is going up. And then, so we use that as a signal to decrease the bit rate on the encoder. And that hopefully preserves the latency, because that's something we're very keen to do. And likewise, we detect packet loss and we back off if we find that we're getting packet loss. And the idea there is to try and reduce the number of freezes to an absolute minimum. But of course, we want to try and raise the encoder bit rate where possible. And like there's this whole kind of art science thing about how do you do probing. For the moment, we're using the fact that the keyframes are quite big and come out quite fast as a way to probe. So we just generate a few unnecessary keyframes, and that will probe the network. It has the downside that if they don't get through, you'll have to generate one more. But it does actually work. It's a nice way of building it up, and there's a reason why we need to do that anyway. Yeah, and this track had 12 different cell IDs, which was kind of interesting. So how do we do all this? How do we sense all this? This is RTCP, which is, in my opinion, the ugliest protocol I've ever worked with. Like it's actually worse than STP. It's got all the like ugliness of the STP thing of having micro formats for every piece of, like every line in STP has a micro format that's different. Well, the same's true for RTCP. Every bit of data you get of RTCP is in another random wacky bit binary format, and that's why it's like SNMP, in that it's a wacky binary format. SNMP at least has a structure to it, which, like, honestly, RTCP doesn't. But all that said, it's very useful. So we use NACS, as I said, and particularly NACS, very useful if your round trip time is at least somewhat less than your latency budget. So if the network isn't the dominant piece of your latency, then you can usually sneak in a full request for a new for a replay of the packet and get it back before your pipeline's emptied, and so that works really well. If you're much closer, if you've got a much shorter latency and it's comparable, if you've got a comparable thing, then you might end up wanting, to use some redundant information and use the bandwidth for redundant information as well. But we're not in that, hopefully. So we actually keep a cache of the last 500 packets, and we just resend from that when we get a NAC. NAC PLIs for sending keyframes. We just force the encoder to generate one. We played with the idea of caching them, but it turns out that actually it's cheap enough to just force the encoder to create one. But we clear the cache and we clear the queue. As the moment we get a request for a new keyframe, we clear the cache and we clear the queue, because nothing that predates that keyframe is any use to anybody except as like filling your pipeline unnecessarily. So, and the only caveat on that is if we've already got one in flight, then we ignore the request, because otherwise Chrome will send multiple requests and just keep sending them until it sees the answer. So we block that. Yeah, and then the other two bits of RTCP are receiver reports. So basically loss and delay, which like I said, we feed into the bandwidth algorithm, and REMB. We're using REMB and not transport-wide congestion control because we've only got a single video source. And so there's really no advantage in using transport-wide CC. And that means that I don't have to implement RTP header extensions, which I haven't done yet. So there's no real need to do that yet. If we end up with multiple video sources in the car, then we'll have to do that, I guess. So it results in a bunch of like bent rules, basically. But it's my stack, you know, do what I want. So we have a small cache, and it's because it's much better not to allow Chrome to do the speed up. At some point, you want it to just give up and start again, rather than like build up a big queue and then play it fast. We only send keyframes when we feel like it. We keep a very long keyframe interval when we can, because that improves the quality for the same bit rate by quite a marked percentage, actually. I mean, it's quite visible that. Like I said, we never resend anything that predates a keyframe. We don't do RTX. This is a cop-out, a total cop-out on my part, but it works, right? We just resend the packet as if it was the packet. We don't wrap it in RTX. That messes up the statistics, but actually it doesn't seem to matter. I don't trust the numbers that REMB give us. We use them as a guideline, but we don't trust them. So we like sanitize them by keeping them within a range that we want to work within. We quantize them so we don't do lots of small steps. We do smaller numbers of bigger steps. And we only do a certain number of steps per minute or whatever. Basically because it's expensive on the encoder, which we'll maybe come to in a minute. Oh yeah, and on the audio, I tweak that with a 40 millisecond P time and 10% forward echo correction. But don't bother with NAC, because there doesn't seem to be any point. Again, this is very kind of opinionated stuff, but given that it's like my hardware and my stack and the endpoints in my control, I don't have to interface with anybody apart from, like, if it works with Chrome, that's good enough in this case. The encoder in here is lovely, but it has some quirks. Like, it won't make some bitrate changes. So I can tell it, like, I want you to encode the next frame at this bitrate, but sometimes it will ignore that without you sending a keyframe, because there are certain transitions you can't do in H.264 without a keyframe. I've never understood what the rules are, but it's like definitely the case. And so it means that effectively many of the transitions you need to force a keyframe, which is expensive in terms of bits. But as I say, we use it for probing whether there's more bandwidth is available as well, which may turn out to be a mistake. I need to look at the stats for that, but at least it's what we're doing at the moment. So we have some standards we do like the WebRTC data channel, which is just lovely. And we use it to talk to a bunch of things on the box, like v4l2. So we control the camera behavior by sending messages over the data channel from the screen, from the viewing device, down to the car and the camera in the car, to do things like maybe change the area of interest. So we can tweak the area of interest to include the windshield, and that gives us better effect on the exposure control, because the camera does automatic exposure control, but you have to tell it what you're interested in to get the results you want. And we also use WIP we use it to rebroadcast the signal. So we have the data comes from the camera to the pit crew directly. But then if there are other people maybe in the trailer or in the team back in the office who want to also watch it, then we rebroadcast from the Chrome browser by adding a WIP output in the Chrome browser and sending it to a WIP service. And the glorious thing is there's a ton of different WIP services. I mean, you can pay for it for some people, or you can build your own with so there's, you know, Twitch and Broadcast Bridge you can pay for. Janice and Ghislaine, you can build your own and run your own. And then there's a bunch of services that specialize in just doing WIP. So Millicast and Phoenix and Cloudflare, and they're all largely compatible. You have to tweak a couple of things, but basically they all work, which means that you get to choose like the price point and how you want to do it. And we're still experimenting with that, but it's kind of interesting. So in terms of like talking, said we talked to v4l2, the kind of rule that we've got is that we don't talk JNI, we don't write C code and link it to the Java, because the stack is in Java and it's nicely memory safe and it's nicely got good thread management and it's got like, you know, proper SBOM. I know exactly what's been built into it. I know what the dependencies are because like Maven tells me. So I don't link to random C libraries. What we do is we run them separately as separate binaries, and ideally we don't even run them. So in the case of v4l2, there's a v4l2 control binary that ships with Linux, and so we use that. And then this is a little class that just talks to that. It sends a command to it and sets and gets values from v4l2 and then sends them back up as JSON. In some cases, they're actually, the thing we're interested in is exposed in sys class as a file, so we can read and write from that directly from Java, but still preserving a nice clean interface. If we have to, we talk sockets, so things like RTP, we'll talk, or if there's a local web server we want to talk to, we'll talk to that socket and then reflect it up, proxy it up through a data channel. And in the most extreme case, we'll talk shared memory to another project, another object. The only case we do that at the moment is the encoder. So we have like a 2-byte shared memory segment that we share between the Java and the encoder, and the encoder reads it before it writes every frame. Before it encodes every frame. And then it looks to see whether we want a keyframe and what the bit rate we're aiming at is. And so that means that the two are nicely decoupled. There's no synchronization between them. And it's a very cheap operation on the Java side to update that. And it's very cheap on the, because it's only a small thing, it's very cheap on the encoder side to read it. And that keeps us reasonably portable and gives us decent memory safety in terms of like the Java front side. However, all of this has led to some quite serious surprises. I mean, the long and the short of it is physics always wins. I was originally a physicist, so I shouldn't be surprised, but I am constantly, actually. So the biggest surprise so far is that the GPS was wrong. Like, we were doing this when we first switched the GPS on. I was like, well, wait a minute. Like, that car can't possibly have jumped the river. And no, it hadn't. And the thing is that GPS in this was designed basically for drinks machines. Like the 5G module is for like static cameras and drinks machines and stuff like that. And it's not expecting to be moving at the speed it was. And what happens is that it integrated the vector of the velocity to work out where it was going to be in a second's time. And in the meantime, the car braked really hard and turned that hairpin corner. And so the extrapolation of where it thinks it's going to be and where it actually is completely different. So yeah, they told me to turn the GPS off because it's like just confusing. I actually still use it to work out which track they're at, but that's about the granularity we can use it for. Yeah, you really do need 4 antenna. Like, this thing has 4 antenna for a very good reason, which is that almost all 5G is actually LTE with 5G added. So you can't get a 5G connection without an LTE connection on almost any public 5G network. Right? It does all the signaling effectively over LTE. It brings the data connection up over LTE, and then it has a look around and says, oh, look, I've got a 5G connection. I can bandwidth aggregate over that as well. So it's like you need the antenna for the LTE and the antenna for 5G effectively, which is like, makes the thing bigger and more nuisance. But it's like, I wasn't expecting that at all, but it turns out to be true. Yeah, who knew it? Race cars are hot. If you mount this like a foot away from a mid-engine vehicle, it gets warm. I mean, so hence the aluminium case for the next version. Uh, there is private 5G out in the world, so not all 5G is LTE-based public 5G. You can get private 5G, and we've tested a couple of them, and frankly, I was a little disappointed. Like, I was thinking that this is going to, like, I put the camera here and the viewer here, and they're both on the same cell. It's going to be like milliseconds between them. And the answer in both the times I've tried it, it's been about the same as on a public network. And I'm like, why? And in both cases, the answer was, well, we run the core in the cloud, and we VPN to it. So my packet is leaving here, going into the local base station. The base station is sending it to the core in Frankfurt or whatever over a VPN. The Frankfurt core is deciding, oh, look, this is a packet for this cell, sending it back over the VPN to the same base station, which is now sending it to the other end. So it's actually real disappointment. I mean, I get it why it's that way, but it's not the time saver I thought it would. Yeah, sometimes, this was a huge surprise, but sometimes 4G is actually better than 5G. And the classic case of this is Macau. The engineer rang me up and said, pinged me and said, like, we're getting really bad results here. And I was like, so looked at the GPS and he was in Macau. And first I thought it was like, well, this is the Great Firewall in a way, and it wasn't. The problem was that they had steel crash barriers on the track. So like, which were absorbing like anything going sideways. They had high-rise buildings, which meant that you couldn't see, like half the time you couldn't see an antenna at all. And they were in a city with hills and foliage. Like, so it's all the worst things. And then the result of that was that the LTE that was at a lower frequency was penetrating those things much better than the high frequency 5G. But the network was saying, hey, I've got 5G, let's use it. So I added a button to switch off 5G, so you can force it to LTE now, if you find yourself in that situation. And the most surprising part of that was rain fade. Rain fade at the higher frequencies of 5G is really significant, and I genuinely hadn't expected that. The other thing to remember is that this is all uplink, so it's how much power this can pump out. It's not like, is the transmitter up on the hilltop being effective in transmitting down. It's me transmitting up that's the issue. So yeah, to coin a phrase from the late lamented Rutger Hauer, it's time to lie. So there's a bunch of things that we end up lying about, just brutally. We always claim this constrained baseline H.264. Like, we always say that's what we're sending. We never send it, but we always say that's what we're going to send. Because if you don't, then the browser will reject the offer. If you say you're going to send it and then you send something completely else, it still works. So it's like, just lie. Likewise with Twilio, as Dan was saying, Twilio does actually support Turn TLS. They claim they don't, but if you make up a URL that has the same credentials as the one they gave you back for Turn TCP, it works just fine. Packet pacing is an art, and what I found is actually, like, everybody says you should do it, but in practice, every time I try packet pacing, it makes the situation worse. So actually, kind of relying on the encoder to effectively do the packet pacing. Now, this may turn out to be a mistake, but like, that's how we are at the moment. So it's kind of not packet pacing. And the final thing is that most of our cars are tourists, right? They're Instagram influencers. This is that our traffic looks most like an Instagram influencer, and or somebody who spends a lot of time on FaceTime. Right? So it's important to get a SIM that's like supporting that use case, and not to buy a SIM that's designed for Coke machines, because like the traffic shaping on that is completely different from what we actually want. So everybody was talking about AI this morning, and I thought I'd mention why I don't do AI. So I trained this robot to drive around a track for a competition. And it, like, basically what it does is it follows the white stripes on the line in the middle of the road, except that I turned up wearing these Converse, and it's thought that it was a white line, and it headed straight for them and then whacked into a wall. So yeah, that's generally my experience of AI, that it doesn't do what you want. So I'm not doing AI. That said, the future of this is actually for supervising, well, I mean, beyond the race car use case, there's a potential use case in supervising autonomous vehicles remotely. So if you've got an autonomous vehicle that gets into a situation it doesn't know what to do with, then the idea is that there's a remote supervisor who can nudge it, like tell it which of the choices it should make. And to do that, they need a good visibility on what it can see, and it needs to be a visibility now and not what it looked like 3 minutes ago. And so we think there's a very interesting market there for remote supervision of low latency video from autonomous vehicles. And we've got a grant, bless them, from the EU Target X project scheme. They've paid us to research and document whether this works and in what circumstances it works. I've done the first set of lab tests, and I'm still working on the data. I haven't actually analyzed it yet, but we got the data earlier this week, last week, and then hopefully we'll get to do some road tests in near Barcelona at the Idiada test facility. We're currently in a kind of odd little disagreement about whether they allow cameras there or not, which is a little bit inconvenient. They do if they're built into the car, but if you add one, they don't. So we're kind of trying to negotiate our way out of that. Or we may have to go and find somewhere else to do it. So if anyone's got a racetrack with 5G on it, do let me know. It would be really convenient. Yeah, but huge thank you for targetx.eu for funding that. It's been a really good way for us to get good data on this rather than making stuff up. How do we do the lab tests? I don't have a Ferrari that I can drive around in Berlin. And even if I did, I couldn't probably do the tests at the same time. So what we actually do is, hopefully, point it at a lava lamp. The advantage of that is, let me make that, let's see if we can make that a bit darker for you, up the contrast. And this actually, that's me sending messages over the data channel to the camera, changing the contrast and the. But what's nice about this is it gives you a random thing that the encoder can't guess. That is moving, admittedly not as fast as a race car, but at least it's changing constantly. And so you get this kind of constant movement. And sometimes it's quicker than others, and sometimes it's brighter and whatever. But so yeah, this is how we, and that is, let me see, that's 5G Deutsche Telekom from my flat in Berlin, and it's getting whatever that is, about 4.5 megabits a second consistently. Fairly consistently anyway. So yeah, and then back to the presentation. How do we lab test? So yeah, if you've been listening, thank you. I'm Tim Panton. Contact me on Tim@Pipe or Steely Glint on KS Social. I do consulting on WebRTC protocols. Those for ICE, SRTP, SCTP, and WIP, we have our own implementations of that are open source. I also do consulting on Panton, GStreamer, Janus, whatever people pay us to do, provided it's interesting. And obviously, I build things with pipe, but the kind of takeaway message is you can't always get what you want, but if you try, sometimes you just might find you get what you need.
Thanks, Tim. Any questions for Tim?
So, well, first of all, I find it curious that the highest limit for drink and drive is your starting point for people getting in race cars. But then also, I was wondering, so I was wondering what is more useful for the people in the pit, if it's resolution or frame rate, because you mentioned 1080p 30, and then you also mentioned frame rates, and I suppose gamers, for example, will go for a lower resolution, as much frame rates as possible to get better info.
The experience is that seems to be a sweet spot. We tried it at 720, and well, so a really funny thing happened when I was in the pit talking. One of the race engineers went on the radio and said to the driver, you're running out of fuel, because he could see the fuel gauge over the driver's shoulder. And so like you need enough resolution to do that, and you need enough resolution to see the number on the car in front and the rest of the signage. And like, I was tempted to go faster frame rates, but it doesn't seem to be that matters. It seems to be like there's a sweet spot there. If they say 60 frames a second is necessary, we'll try building it, but it hasn't. It seemed, but at the moment we're better than anything else, and so that'll do. But yeah, still to be decided, I think, to some extent.
Thanks.
Maxime first, then I'll come back.
Hey, team. Great presentation. I'm just curious if you considered other technologies, not 5G, to provide this kind of link. Because if it's just a racetrack, I guess you can just deploy kind of local Wi-Fi or something like LoRa or something.
So Wi-Fi, we did think quite hard about, but like these tracks are typically a couple of kilometers in diameter, and things like the Nürburgring are long and thin. So you'd need to like have a mesh Wi-Fi, and you'd need multiple towers, and like things get complicated. What you do find though is some of these tracks have dedicated connectivity for the broadcasters, but we're not allowed to access that, or we'd have to pay an enormous fee to do it. Whereas the 5G is, like I said, €8 a day. So like, if we can get what we want out of 5G, then like, why would we bother with anything else? We have looked at very specific use cases that are smaller or indoors or like some other like criteria, and then maybe Wi-Fi is the right answer. But for this scale of thing, 5G is just great.
Yeah, but you're clearly having some issues with the packet loss and the stuff you cannot really control. Like,
no, you just have. So you have to.
And if it's mountains, you probably don't have like such good coverage. I mean,
you have to get your NACs back. You have to respond to the NACs quickly enough, basically, and have enough pipeline to do that round trip time. But that seems to be, within the 200 to 300 millisecond latency budget. The 80 millisecond round trip time is low enough that you get away with it. Is the experience that we've got.
Cool, thanks.
Great presentation. A couple of questions. Why H.264 base buffer, and why not?
Why
did you use H.264? Yeah.
Because the hardware encoders exist at low energy consumption. Like, I've looked at AV1, but this hardware would do AV1 probably in real time, but the energy budget would be up into the like 20 watts or something. And like, it doesn't seem to be necessary, basically.
The second question is, you said that you do a whip from the browser of the pit?
Yes.
Why like that, and why not a centralized server or something like that? You do a whip.
So yeah, maybe I should have done a better architecture diagram. So the idea is to do the idea is to limit the latency as much as possible in the first hop. The people who are really paying for this and who really care and who will notice the latency absolutely most are in the pit or in the trailer. And so we're deliberately removing a hop there. And that means that we do the first hop direct to the user's browser. The downside of that is that I don't want a second stream from the camera up to the cloud because that halves my bandwidth. So what I in fact do is to run it from the browser, re-encode it in the browser into whatever it is that the cloud service wants and resend it. Net result is about another 100 milliseconds latency, but those people are far away and they, like, if it's 400 milliseconds, they honestly don't know. Like, the only exception is if you have somebody who's in the stands of the racetrack on their mobile watching through the whip stream. They will maybe notice that extra 100 milliseconds. But in tests, what we found is that the time it takes them to look up and look at the car, they can't tell.
Thank you.
Thank you, Tim.